The speaker's worst fear is like disappoint a full room as the absolute worst possible. So we've had yesterday this nice, these nice puzzlers with would-be interview questions for C++ programmers, and God, I wouldn't have made that job. I wouldn't have landed that thing at all. But I assume one of the interview questions that you would be able to answer, Celine, would be implement a binary search for me, please. Can you do this? Could you sit down and implement under interview pressure binary search? I could try. Okay, that's an excellent answer. So we're going to talk about today about binary search, and no worries if you forgot the nitty-gritty of it. We're going to recap them, and it is with great trepidation that I must say that I think there is one rough edge in binary search, even though we have literally used it for millennia. In binary search that needs to be improved. With that, let's proceed with my unwilling obsession, my reluctant fascination, my careless craziness, which is improve on consecrated. I didn't sign up for that. I didn't want to do it. It just so happened. So back in 2014, I defined two algorithms for string-to-numeric conversion. And they're today part of Meta's Fali library, but they're not part of the standard library implementations. As far as I know, they're quite a bit faster than the classics. 2017, I published a paper in an algorithms conference, fast deterministic selection, in which I showed that an algorithm can be written that does a lot better than GCC and Clang's implementations of nth element. But apparently nobody took notice. 2019, I discussed a faster STD make heap, quite a bit faster than the original implemented in the three major implementations of STL. I discussed in CVPCon 2019 talk. Nobody noticed. Somehow I'm starting to think, whose arm should I twist here to get people's attention? Then the pandemic came, which has no link to anything at all, but I had to fill those things. 2023 September, which is today, we're going to discuss about the better binary search. So that is the history of how we got here. The history of binary search itself is a lot more interesting, and it originates. I look like what was the first binary search ever described, and it turns out it has quite a long history. All the way from the BC era when they counted backwards. I mean, come on, you're born like year minus 400. How did you know? Right? Yeah, I mean, born in year minus 400. I'm gonna live until like 335, and that's gonna be my life between these two negatives. This is weird. I have no idea how those people did the calendar thing. That was a joke to the people in the back there. Okay, so Archimedes is known to have used the method of dichotomies, and that is a very close cousin of binary search. Essentially, in philosophy, you're looking at dividing sets into two, and Archimedes figured out that the better close in size the two sets are, the better, right? So you want to divide sets into two roughly equal parts, so then you can dispense with one half and then focus on the other half, and repeat that method a number of times. Euclid did the same with a number of geometrical and mathematical proofs. Socrates, Plato, Aristotle, Descartes, like dichotomy and Descartes were very kind of one item. So Descartes applied method of dichotomy everywhere, for better or worse. And then in math, per se, sort of the first clear note of bisection was by Bolzano in the 1800s, and then it became more formalized in the 20th century. Binary search, the first mention of binary search was in one of the Jatakas. Who knows what a Jataka is? All right, for those of you who are not experts in Buddhist religion, I'm not, but I have Google, and I have the advantage of like knowing, searching before you guys, right? So essentially, in one of the stories about, the previous lives of Buddha, there was a description of binary search. It was, you have these families, and you divide them in two, and you divide the remaining families in two, and so on, until you get to, I don't know, one guy and you kill him, or I don't know what happened then. So, but it's kind of funny that in 1946, okay, this is not working. It's kind of funny that in 1946, Mauchly published an actual implementation of binary search for computers. So it was the first advent of an actual binary search algorithm that was exactly meant for computer programming. And the funny thing is, it only worked if n, the number of elements searched, was exactly 2 to the power of n minus 1. It did not work for any other size. Which is kind of funny. I mean, come on. I mean, you got to run for other sizes as well. It turns out if the number of elements searched is 2 to the power of n minus 1, if you have n 2, you get 2 to the power of n minus 1 minus 1. And then that makes the whole analysis very easy. But if it's not, they didn't know what to do. And if you're like me, you're thinking, hey, you know what? I wish I would travel back in time to year like 1946, and I would show those nincompoops how it's done. I mean, come on, you do the approximate, divide by 2, and you get like, you get like just a bit off the median, and you move on, and you're gonna amaze everybody. It's gonna be like, oh my God, oh, did they come back from the future, right? So the power of the algorithm is you eliminate, so this is kind of the interesting tidbit. You eliminate as many elements as possible. Don't focus on finding something as you would do in a linear search, like, oh, is this the guy? No. Is this the guy? No. Is this the guy? No. So you focus on actually collapsing the search range. You're looking at collapsing the set of elements you look at. And that's the beauty of the algorithm. Now, do I care? We're not going to improve binary search by 2x. We're not going to improve it by an order of magnitude. We may improve it by a couple of comparisons. Don't forget there are very few comparisons to start with because binary search is in log 2n, which means if you look at 1 million elements, how many comparisons are you liable to do? Who said 20? What? Who? 1 million elements. How many comparisons do you do? Log 2 of 1 million. All right, folks, important numbers in computing. Powers of 2. To the power of 10, 1,000. To the power of 20, 1 million, right? Roughly. Right? But, we'll do approximations. So, 1 million elements, you're looking at 20 comparisons or about, right? So if you shove off 1 or 2 of those 20 comparisons, you're going to get, 5 to 10% improvements on an algorithm that's been like there for 4,000 years. I mean, that, I would sign up for that, right? I'd be happy to do that. Now, look at this, however, because some people may be at, computers are fast enough and, all those good things, but come on. We already are the goddamn Scrooges of computer science and engineering. We are the people who don't check bounds access on vector. We're the people who don't do null check on STD shared pointer and, all smart pointers in the standard. We are the people who define the STD optional, of which only purpose is to be like optional, but then we don't check that it's there. The irony of this and the fact that the people in the standard did not figure out the irony of this, which makes it squared, baffles me. Right? Consider this. Let's define a type that is going to be safe to optionally store something in there. It may be there, it may be not. Okay? Are we there? Are you with me? So the whole purpose of the type is to be an optional presence of something. And then they said, how do we access that thing? Oh, I know. Let's define an operator arrow, which by itself is kind of a bit, come on. That's not a pointer, but let's roll with the punches, as they say, right? So then we say, okay, so I'm going to define this awesome operator arrow that's going to give me the optional value for which I built this entire facility. And then, I'm not going to check that. I assume it's there. Okay, so who uses C++ in this room? Okay, we are those people. Okay, we are the problem. Okay? Now, fine. Optional. And the list goes on, and the price we pay is steep. It's kind of a problem that we are so happy about the last bit of efficiency that can't be even demonstrated. Because, come on, I mean, let's face it. The null check in a smart pointer is going to have a 100% success rate. So it's a very easily predictable test. Right? You know the branch predictor? So there's a branch. There are multiple branch predictors in today's computing units. And the way branch predictor works is if you don't take a specific side of the branch, it's just going to predict, and next time it's going to do the same. So for a null pointer check, that branch predictor is going to have literally 100% success rate. You know I know that? Because the time, the one time is going to not succeed, the whole application is going to fail. Right? So it's like, it's like, one of those jobs, like, I'm a mountain climber. Or I'm like, one of those people who work with bombs, like the bomb diffuser or whatever they call it. They can make one mistake in their career. And then you're done. So that's that test, right? I know it's a little dark for you. Sorry. Okay, so I do care about saving those couple of comparisons from out of 20. Yes, I do care, and you care too, even if you kind of don't know it yet, right? So today we're going to look at no-risk performance improvements for STD binary search and friends, and let's see how we can do that. All right, this thing works on like within 5 centimeters. Okay. So we just talked a bit about introductory items. So let's look at binary search, the absolute classic algorithm. I call it the violet's eyes version, which is, I don't know about you, but it produces an emotional response in me. So I go to college, and I see this first time, and I'm like, I don't care about dating. This is going to be my life. I'm not kidding. So I'm looking at this, and I'm thinking, this is the most beautiful thing I've seen in my life. The violet eyes algorithm. It's so beautiful, so symmetric, so simple, yet so powerful. It just, I'm not kidding. My hair is raised right now, and I feel like the hair in my back of my head is like just weird. So it's just an algorithm that has its own simplicity and beauty that is just amazing. You can't like this algorithm and have a 9-to-5 job. It's just gonna go, oh my goodness, I'm gonna lose sleep over it. The way it works is obviously I'm going to take 2 iterators, and I'm going to take a value to be searched. And my attempt again is to collapse the range, the search range, as much as possible. So with each step I'm going to do, well, let me take the median point. I assume the range is searched, and I'm going to go to b plus c minus b by 2, which is the damn straight middle of the range. I'm going to look at that element. And if I fall on the left, if I fall on the right, I'm going to throw away 1/2 of the search space. And that's the power of the algorithm. I'm going to reduce the set of things I'm looking at in half every time. And in the happy case, when it's neither smaller nor greater than, the median is neither smaller nor greater than the sort value, I'm going to know that I'm right there, and I return true early because I found it. And that's binary search. Okay? So that's actually a very nice thing, and I invite you to think about, for example, things like how often do I get all the way to the end of the binary search? And the answer is actually in half of the cases. In half of the cases, I'm going to have to collapse the search range all the way to 1 until I make a decision, simply because the way the binary division works, for example, all odd elements, I'm going to look at them in the last step. So even though I do return early, it turns out that very often I need to collapse the range all the way to the bottom before making a decision. And after the range has collapsed entirely, I'm going to decide that I did not find this element. I'm going to just return false and be on my way, right? Now, if you look at, if you crack open your standard library implementation and look for, there is an algorithm called STD binary search, which has the signature. And, let's take a look at the STL implementation. Does it look like this or not? Do you think it's going to look like this? Okay, one nod, negative nod, one hand up. Okay, why do you think it looks different? Because C++ makes everything more complicated. All right, so first of all, like it has a lot of double underscores. There's going to be a lot of double underscores in the whole thing, right? And then there's going to be a lot of just aggravation for a variety of reasons, some of which I agree with, some of which enrage me, but let's pass on, right? Let's go over that. But actually, there is an algorithmic reason for which the STL implementation is different, which is the following. Take a look at the following. Let me go back one slide here and show you the following. Each pass through the loop, I'm going to do two comparisons, v less than star m and star m less than v. So that's two comparisons per pass. It turns out if you compare things like integers or pointers, those two can be actually one comparison because I'm not sure about your assembler knowledge, which mine is terrible, but I do remember vaguely that you do a compare and then it sets flags. It's greater, it's smaller, it's whatever. So you do one compare and then two jumps. So you compare only once and then you do two jumps, right? That's not generally enough. For example, if you compare strings, it's not going to work just as nice, right? So in the STL, they said, hey, you know what? We're going to take a predicate here. So I'm going to use this p, and less is the name of my predicate, which is like a function that compares two things, and it has the semantics of less than, right? So let me, instead of saying that less than that, I'm going to call this function less against the two values, and I'm going to make decisions based on that. Now, the STL wants to minimize the number of calls to less. And now you can see that this previous algorithm, the violet eyes, has a disadvantage, right? It calls less 2 times per iteration. And that's kind of, even though in some situations, in some cases, it just do one comparison, it turns out that STL wants to minimize calls to less, and therefore it uses a different algorithm. This is a slightly different algorithm. It does not have violet eyes. It's not as symmetric and beautiful as the other, but I like it nevertheless. And the way it works is, again, it cuts the range to be searched in 2, so b plus c minus b by 2, and then it makes the following decision. If the median is less than the value, then I'm going to advance the beginning pointer all the way past the median, because I know that it's impossible that what I'm looking for is going to be on that side, right? Otherwise, I'm going to set the end to the median because I know that there's nothing interesting on that side of the median. And then I'm going to continue with the new begin and end, right? The point here is that I call less only once per iteration, but I don't have an early return, so I always go log n steps all the way to collapse of the range, not of civilization, okay? So I go all the way until b becomes equal to e, and then I make my decision. Did I find the guy or did I not find the guy? And the decision on whether I found or not is, well, did I go all the way past the whole range? And I know already that star b is going to be star b is not going to be less than v, and now I got to check the other side of the test, which is v less than star b. So I checked one way, I checked the other way. In the previous algorithm, I did it every iteration, right? So I did 2 tests, is that less, is it greater, and whatever. But in the second case, I do only one less in the loop, and at the end, I do one more less. And it turns out that if you count the number of calls to less, this is better. So therefore, this is in a standard library with the appropriate double underscores and all the good stuff, right? Awesome. So actually, this is called lower bound, because lower bound is a more useful function than just binary search, because it gives me information. Binary search says, found it, like a Boolean, right? Gives you a Boolean. Found it, oh, no, it's not there, right? But actually, if I want to insert, if I want to do something, if I want to look for an approximate value, if I want to insert a new value in the thing, if I want to know the approximate position of where that guy would fit, I would need more information. And that's where lower bound comes into play, because it returns the position to the left of which everything is strictly less than. So it gives, I'm looking for, I'm looking for 42 within like a number of integers, and it returns me the position that I know for sure to the left of that position, everything is less than 42, 41 or less, right? And this algorithm is very much like the other one. In fact, the implementation in the STL just calls lower bound and then has one more line. So literally it's 2 lines, right? So lower bound is going to, again, do the same strategy all over again. And this is the algorithm that is the most informative. And then we have upper bound, which is everything to the right of the upper bound is strictly greater than my value, right? So I have I can search, I can search, give me the position at which I know there's everything here is smaller, and then I can give me the position such that everything here is greater, and then there's what's in between. Equal range. In between, everything is equal to your value searched, because there could be duplicates, right? And it turns out that there's a fourth algorithm called STD equal range, which gives you that exact range of equal values within the searched range, okay? Now, the thing with equal range is kind of funny, because you could say, why do I need equal range? I could compute lower bound and then compute upper bound and be done with it. It turns out that there's more to the story. You can implement a more efficient equal range if you search for both simultaneously. Okay? We're going to get there. Fear not. Okay, so let me get to 5 centimeters of this thing. Okay, it does work. So to evaluate the, how good, how well am I doing? Like, how good am I at searching things? We gotta discuss the expected number of comparisons. So apologies for the bit of math here, but the expected number of something, you sum, or you take the integral if continuous, but you sum in our case the number of comparisons with the probability of that event. Like, okay, if I have an array of 10 values, I search for the first, I count the number of comparisons, the probability is 1 by 10, assuming I'm searching for all 10. I'm looking for a second, I count the number of comparisons, what's the probability, I multiply with the probability, etc. If all are probably equal, then all probabilities are going to be the same, which is 1 by n. So the probabilities are kind of, we can simplify, at least in first approximation, we can think all searches are equally probable, right? So that's what we're going to use as our benchmark, the expected number of comparisons. Fine? Now, the question is how we design a fair experiment, because some searches are going to succeed and some searches are going to fail. How many are going to succeed and how many are going to fail, right? What do you think would be a fair experiment? I'm going to go back so you don't read the slide. How many searches do you think would be a fair assessment of binary search? I have n elements to be searched. A fair assessment of the average number of comparisons per search. All right, any ideas? Do I search for all the values in the set? Do I ignore a few values? Yes, please. Sorry? 3. 3 searches? Okay, what would be the 3 searched? In the middle? Oh, no, I'm testing now. So I'm testing, I'm saying, I want to count how many average comparisons. Yeah, it's not the algorithm per se, but it's the experimentation with the algorithm we're looking at. So restating the question, I have n elements to search in a set, and I want to say, how good do I have a binary search algorithm? And then I say, I'm going to design an experiment. Am I liable equally probably to search for every element in the set? Would you agree? Yes, thank you. Thank you. So I have n searches that are going to be all successful for each of the elements, right? But then I'm going to have unsuccessful searches. How many is for a good experiment? How many unsuccessful searches should I have in a well-designed experiment? Okay, information theory. What is the most information you can extract from a binary event? 1 bit. How do you extract 1 bit from something that is probably with 50% one way, 50% the other way? So if you want to design a good binary search experiment, you're going to have as many failed searches as successful searches. That way you extract maximum information from binary search. You get 1 bit of information. If you have more successful searches than unsuccessful, that would mean you're biased toward the success, otherwise you're biased toward the failure. You don't extract 1 bit of information. So the absolute immutable truth we're looking at here, I'm going to have n successful searches to experiment with, and equally n unsuccessful searches that I'm going to be looking at. So far, so good. But now I ask you a different question, which is 5 centimeters. Which is, I'm kind of obstinate in using this thing because I think it's cool, but it's kind of the range is terrible, right? And it's charged and everything. So I ask you a second question. Of the failed searches, how many cases do I have of distinct failed searches? So I may search for something that's somewhere in between, in the wrong place, right? So I have like in the array, I have like number 42 and number 46, and I happen to search for like 45. And it falls in between the interstices, right? And I have the case in which it's all the way too small or all the way too big, right? So I have 3 cases: too small, too big, somewhere in between, right? And one, other question would be, okay, so I have like n failed searches. How many of these are going to fall too small? How many of them are going to be too big? And how many of them are going to be just in between? So this is kind of, this is where I protest. Because, this is kind of an important distinction that we should make about binary search. Like, how do we handle those unsuccessful searches? So let's look a bit at the distribution on an example. So I have this sorted array from 188 all the way to 705. And I have a number of searches with colored shapes up there. And of those, I'm going to have the green ones are matches. So I'm searching for the exact thing. The red squares are going to be failures in between. So they're going to be equally probably in between every 2 elements. And then I'm going to have a few triangles that are a bit kind of out there because they fall outside the entire search bound. And those are the things that make me unhappy, right? So we're going to have 50% successful searches, as we discussed. 3 failure cases: search for value in between the existing values, search value smaller than the minimum, 188, and search value larger than the maximum, which would be 705, right? Now, the traditional experimental analysis that you're going to see in all theory books is going to have, I'm going to ascribe equal likelihood in between or too small or too large, meaning there is only 1 triangle here and 1 triangle there. And it makes the math easy, it makes researchers happy, and it makes practitioners unhappy. Why am I unhappy? Because it turns out that very often we do search for out-of-bounds values, something that theoreticians don't, ignore. And actually, this whole idea started from looking at, in an application at NVIDIA. I was looking at the the searches in a binary search, and I was like, a lot of these go outside the bounds, and those are the worst case. I mean, come on, there's got to be something there, right? Let me give you a few examples of cases in which we do search for out-of-bounds values with some frequency. The stored values in the array are grouped, but the search values are scattered. For example, we have theoretical measurements versus actual measurements. Actual measurements are always going to have outliers that fall way outside the bounds. That's one case. In a practical application in stock market options, you compute something in theory, and then you look at the actual expirations and strike prices, and again, you may very easily fall out of bounds just because it's not a fit for whatever you're theorizing. I have a special list of things like reserved, allocated, assigned IP addresses. And I want to search my IP address, whatever IP address I'm browsing to, with a small list of reserved values. And it's very likely that my values, which are like 169, whatever, are going to be either to the left or to the right of what I'm searching. Always when the search set is small, I'm going to experiment this out of bounds search, simply because there's a lot of likelihood that there's a lot of sets, a lot of values outside the search range. So of course, we still care about speed, even if a search set is small, because we may search these small sets very, 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 very many times. So, I'm not, I don't care that it's small. I still care about saving a few comparisons there, right? Special values in a list of integrals, words, searching for pointers in an array of allocations. So actually, binary search is used in a number of allocators. Did this allocator allocate this particular pointer? And if I have these, pre-allocated pointers sitting in an array, and then I come with a wild pointer from a different allocator, whatever, it's going to be outside the bounds guaranteed, right? Even for data that is Gaussian distributed, don't forget that there's a 32% choice my search data is outside one standard deviation, and 5% it's outside two standard deviations. So if I select my data from a Gaussian distribution, if it's grouped enough, I'm going to still have a lot of searches outside the search range. Many of the fat tail distributions, so this has been, there's been a lot of talk about like the fat tail and the heavy tail, all of these long tail of internet commerce and all that stuff. And they show distributions that fall, like instead of falling exponentially like that, they kind of fall, and they kind of, the density here at the tail is quite high, the density of probability. So I'm liable in these distributions to search a lot of things that are outside the natural range. So this is the point of contention. I will argue that there are quite a few more times I'm going to search for things outside the range stored in the array than the theory dictates. The theory says you can search one value on the left, one value on the right. So you have like two cases, that's it. You're done. Everything else is in between. And I very much disagree. Now, this would be what the theory has. As I told you, there's one triangle on the left, one triangle on the right, everything else is in between the red squares, and then I have the green squares, which are the successful searches. So that's my experiment, right? The proof of binary search optimality is done on this case. And I argue that this case is not entirely realistic. I am more liable to have values in the triangle area than inside. Okay, so now let's go to my extreme situation, which is everything that fails is outside the bounds. Like everything I look for there's nothing in between, and this is like everything that fails is gonna be either way to the left or way to the right. This is an artificial example, but let's design an algorithm that will work well for that case. How would you design a binary search for this case? Yes, please. Store the min and max. I mean, you can look at b and n minus 1. Yes. Who agrees? Who disagrees? All right, so let's remember thank you very much. Let's remember the very purpose of binary search. Eliminate as many candidates from each comparison as possible. If I look at the extreme left, how many candidates am I going to eliminate? The red triangles on the left, which is n by 2, because I have like n failed, n successful, n by 2, and n by 2. How can but I also I don't eliminate any of the potential successful searches, the green bullets. How do you draw a vertical line that is going to eliminate as many as many shapes, green or red, from this image as possible? If, as was suggested, you're going to draw here, or let's say the beginning, right? If you're going to draw here, you can get rid of these guys, right? But these guys are still, you're going to still look at them. So eliminate out of 2n possibilities, you eliminate n by 2. Can I eliminate more? What if I go here? In the very middle. In the middle, I have two advantages. Number one, I'm going to eliminate half of the whole thing. Green and red, they're all gone. So the first shot is always best in the middle because you get rid of literally half the elements. So if you search for 2n elements, you're going to get rid of n. And number two, the next step, you know if you want to look at the right bound or the left bound. You don't need to look at both. Oh, sorry, I pressed this by mistake. Okay, so this is the key. First shot in any binary search, you cut down the goddamn middle. If you remember one thing about binary search from the stock, first step, you always cut in half. It's like pizza. You just, you want to just cut in half and then think about the rest. That's your planning, okay? Because if you cut in half, you're guaranteed to eliminate half of the uncertainty, right? And then, second step, am I on the left? Oh, let me look at this guy. Am I on the right? Let me look at this guy. And you eliminate another n by 2. And that's how the cookie crumbles. So for this extreme case, it turns out that the best algorithm is cut in half, get rid of half the pie, and then look at the extreme that's left. And that's how you eliminate, and then continue with the standard, the classic binary search. So that would be the optimal algorithm for this case. Remember, it's an artificial case. This is not the final algorithm, right? But it gives us a thought about, wait a second, maybe at least in a few cases, the standard binary search is not what we're looking for, is not our best tool, okay? So for this extreme case, okay, so we just discussed all this. So the optimal algorithm will be to, we just discussed all this, so it was all in talk. Let me calculate real quick what would be the probability of us doing well if I actually use the classic algorithm. It turns out that the second step is wrong because I'm going to eliminate only 3n by 8 elements instead of n by 2. So that's quite problematic. So we don't want that. We want the algorithm as follows. In blue, I show the comparisons. So remember, lower bound extreme. If begin is end, I'm done. Then I compute the middle of the range, the median, and then I'm going to compute less of median and value. If it's less than, then I'm going to go to the upper half. So the median is less than the value. So I'm going to go to the upper half, and then I'm going to look at the very last element, less last value. And then I can do an early return, and I'm done. Otherwise, I go to the lower half, right? And in that case, I'm going to compare value against star begin, which is the first element. And after all of these two steps have been completed, I'm going to proceed with the classic lower bound because I know the bounds and it's optimal, right? So optimal algorithm for this extreme case, all failed searches are way outside the bounds. Cut in half, get rid of half, look at the first element or the last element, get rid of half more, and then continue with the classic, okay? But that's not the way it happens in the real world. In the real world, you're gonna have some outside and some inside. So let's look at the actual best way to go about a binary search that works in all cases. There was a question from the audience, which was, if I know that I'm liable to search out of bounds, can't I just look at the beginning, end, or the end? And the answer is, that would be suboptimal. The thing is, if you cut in half, then you only need to do one more test. If you look at the bounds, you need to do 2 tests. 2 is greater than 1. QED. Okay, this laughter almost brought down the house, folks. I mean, come on. Keep it down. Keep it low, okay? We're going to bother people in the other rooms. So you don't want to look at the lower or upper bound first. You want to look in the middle, and then you eliminate half of the cases, and then you look only at one. So by definition, you're doing better, right? Awesome. So let's see the trade-off where it falls. So remember, the one extreme case would be I'm going to have essentially nothing outside the search bounds, and in the other case, I'm going to have everything outside the search bound. So what would be the trade-off here? In the classic algorithm, I'm going to cut at half first and 1/4 next. In the extreme case 2, which was the artificial case we just discussed, I have very many out-of-bound searches. So I'm going to cut at 1/2 first and then 0 distance from the bound next. So, okay, you're an engineer. So looking at 1/2 and 1/4 versus 1/2 and 0. So, okay, so, in one extreme case, I'm going to cut in half, like 1/2, 0.5. And the other case, I'm going to cut at 0, which is like 0/5 or whatever, right? So it's either 0 or 1/4. What is straight in the middle of 0 and 1/4? 1/8, thank you very much. Norwegians are good at math. Okay, so if I got you to chuckle a bit, I'm amazed. That's fantastic. Okay, so it's an engineering decision, but it's a principled decision. It's not an arbitrary decision. In one extreme, I choose to cut at 0. In the other case, I choose to cut at 1/4. And I have no idea, no prior idea about the distribution of actual searches. So I got to choose something in between these extremes. What can you choose as an engineer that is the best between two extremes? You're going to choose the half. You're going to cut at 1/8. So instead, it's like a binary search. Instead of cutting at half all the time, you're going to start by cutting at 1/4, right? So this is the idea. We have no idea how to do, so we're going to cut at 1/2 and then 1/8 from the first bound, which is 1/4 of what's left. So instead of saying, size is begin minus n whatever by 2, we're going to do by 4 and work from there. So let's take a look. This would be called the bounds leaning binary search. Bounds leaning, it means it's always going to lean toward the bounds because you're cutting, instead of cutting in half, you're cutting somewhere closer to the bound than half, which is at 1/4, right? So this is the important tidbit. Here. So I made it a different color. I was a bit surprised. Do you distinguish this color? Okay, it looked a lot better on my laptop. I mean, it's supposed to be like red, right? Okay, so here I'm going to be in the upper half, so I cut at 3/4 of, because, obviously I'm going to go 3/4 because it's 1/4 from the end, right? So I'm going to go 3 times c minus b by 4, and if I stay in the lower half, I'm going to cut at b plus c minus b by 4, right, as I promised. So my search is going to diverge quickly toward the bounds of the search. And once I decided that actually, I found something that's less than, in that case, I break and I complete with the classic lower bound, which is going to be optimal for what's left. So the way this works is, let's take a look at the successful search. So let's look for 394. So in the classic algorithm, I'm going to cut first at 498, and then I'm going to cut in half at 362, and then again in half at 412, and finally I'm going to fall on 394. So that's the classic algorithm. With the other algorithm, I'm going to cut first again in half at 498, but then I'm going to go a bit lefter than 8 by 5. I'm going to go all the way to 8 of 2 to 67, and then luckily I found the value in only 3 searches, right? So that's a good case. There are cases in which we do one more comparison. In the case of searching for 412, again, we're going to cut here in half, and then we're going to look at 362, and then we're going to look at 412, and we found it. With the new algorithm, we're going to go from 498 all the way to 267 again. So that's a bit too far. So I'm kind of taking a risk by going away too far from the search element, and then I'm going to do 2 more comparisons, and I found it. For the unsuccessful searches, Again, the classic algorithm also always cuts in half, and then it's going to go to 32 and in 3 steps it found the mismatch. And in the other case, I'm going to do one more comparison. Now, if we search for something that's out of bounds, I do expect to do better than the classic algorithm because I'm going to go real quick from 498 all the way to 214, and then I'm going to essentially find that it's missing from the array. So out of bounds searches are always going to be better with the new algorithm. All right. So as we discussed a bit in the beginning, there's another algorithm for binary search, which is equal range. And this is where things get really interesting. And this is the most exciting part, actually. I saved it for the end. And it goes the following way. Okay, equal range. Find me 2 iterators such that everything here is less than, everything is greater than, and what's in between is the good stuff. And if there's no good stuff, the range will collapse to, it will be like a 0 length range, right? So that's equal range. We are engineers. We already have lower bound and upper bound. So the straightforward approach would be call lower bound, call upper bound. Yay, right? But it turns out that today's STL implementations do a bit differently. They start with a violetized algorithm that we discussed in the very beginning, and they cut the range in half, and they cut the range in half until they find some iterator inside the found sequence, inside the equal range. And then they use lower bound and upper bound to find the bounds. Can we do better? And to get the answer to that, let me ask you a question. Okay, let's say you have an array of 1 million elements. And let's say we search for equal range of, let's say it's integers, between like 1 and 1 billion, and there's 1 million of them, right? And let's say we search equal range for number 500,055. All right. Question. How many of those equal values am I bound to find? Am I likely to find? I may find 0. I may find 1. I may find 2. What's the most I can find? Thank you, 1 million. So I can find 1 or 2 or 3 or 4 values up all the way to 1 million. These are possibilities. So equal range could return a range that is wide, like 0 elements. I could find 0. Sorry, I forgot about that. So I could find 0 elements. I could find 1, 2, all the way to 1 million. Now let me ask you a second question, my friends. What is the likelihood of me finding 1 million equal values? Is it the same as me finding 0, 1 elements? Okay, somebody laughed, I'm not sure why, but I see a lot of nods to the negative, right? It's like, if I have 1 million elements, I'm more likely to find a few that are of the same value as opposed to 1 million. However, my friends, these two algorithms, the STL algorithm, assumes there's equal probability of finding 1 or 1 million elements that are equal. In reality, what happens is that there's a lower probability of me finding more. The more elements you find, the lower the probability. If you find 1, you have some probability. If you have 2, okay, that's a lower probability. If you have like a 1,000, that's a much lower probability, and so on. So usually in all distributions that I know of, Gaussian, uniform, zip, power law, fat tail, whatever you do, you're going to see that the probability of finding a bunch of equal elements is a lot lower than the probability of finding a few equal elements, right? And actually, equal range is designed in a way, surprisingly, to assume that I'm just as likely to find 1 million elements as 1, as 0, as 5, as 500. So that's not cool. So we don't want to have equal probabilities for these things because in reality, they never are. Most real-world data is not like that. Most theoretical data is not like that. Like most data you can find is not going to be like that. And I'm going to propose to you 2 solutions, which is, one is Galloping search and one is left-leaning upper bound. They have cool names, right? Galloping search, I mean, what's going on? Where did horses enter the equation here? Like, what's with the horses, right? And left-leaning, what's with the communists? Right? I mean, come on. So I'm going to show you one thing about I'm going to show you Galloping search. This is not my preferred algorithm, but I think it's a good algorithm to know. All computer theorists know it very well. Very many people in the industry do not know it well. How many people heard about Galloping search before today? All right, the people in the back are always the smartest. Yes, thank you very much. Yes, Victor? Okay, so just a few, which makes my point. Galloping search is a very interesting algorithm because it works very well in certain situations. It works like binary search, except it starts from one side. And I'm looking at the next element, step 1. And I don't find it. It's like still less. Then I'm starting to lose my patience. I make 2 steps. I take a step of 1, and then I take a step of 2. And if I still don't find it, I'm continuing to lose my patience. That's the gallop part. I'm going to make 4. I take a jump at 4 steps. And essentially, I'm doubling my step with every step of the search. I'm doubling my gait, right? Which is kind of unfair to horses because horses don't do exponentials very much, right? I mean, come on. But, it's like a horse that starts to gallop, right? So I'm starting with 1, and then 2, and then 4, and then 8. And all the way, maybe at some point, I'm going to overshoot the goddamn range. And I'm going to be very unhappy. But what I do next, I'm going to be, okay, so I overshot. So I'm going to continue searching in the remaining range using classic binary search. And that's what Galloping search does. So you start from one side, you continue with increasing gait until you overshoot or you find the value and you're good. And the last steps you're going to take by using classic binary search. So that would be the Galloping lower bound. And again, there's an integer in there that you can see that it's where's the promised thing? This is the thing, step times equal 2. So you always multiply the step by 2 in searching for the thing. However, this works best, is optimal if you have an exponentially decreasing likelihood of equal range being larger. And that's only a subset of all distributions. Again, I'm an engineer. I want to do the right compromise. What is the right compromise? Communists. Left-leaning upper bound. So to search for the equal range, I'm going to do the classic lower bound, the improved lower bound first. And then I'm going to do a left-leaning upper bound, which is the following. It looks like upper bound, except I cut at n by 4 all the time. Why do I cut n by 4? Because I want to be, so I got the lower bound, and then I don't want to search in the middle because that would give equal likelihood to everybody. I want to search somewhere close to the left bound. So that's why it's left-leaning. I'm leaning to the left. I'm cutting at 1/4 instead of half. So that way, I'm giving more chance to short ranges of equal elements than to longer ranges of equal elements. So the combination between lower bounds leaning lower bound and left leaning upper bound would be the best for equal range. With that, let's look at a couple of experiments. So here I have the unhappiest case for the new algorithm. This is the happiest case for the new algorithm. And as you see, we engineered the whole thing carefully in the sense that we do have a little loss. This is the number of comparisons, up to 1 million elements. As I promised, about 20, right, is the maximum. We do have a small loss, like half a comparison on average, for the worst case for the new algorithm. But in the happy case, we have a very good drop in the number of searches for the new algorithm. Number of comparisons, right? But this is unfair to the old algorithm. This is unfair to the new algorithm. So I combined the two, and I showed how about we have 75% inbound failed searches and 25% 12.5 and 12.5 on each side. And in that case, I still have a significant gain of a couple of comparisons per search. To conclude, sorry? Lower bound. This was lower bound. Equal range is more difficult to kind of experiment with because you gotta do searches for every number of equal elements. So you can arrange your experiment any way you want in some ways, right? So that was lower bound or binary search or upper bound. So for lower bound, upper bound, binary search, first cut I have, I hope you remember this, always first cut in half, and then you cut at 1/4 from the extreme, up until you find something bounded, and then you continue with the classic. For binary search, you use STD lower bound. For equal range, you use lower bound, and then you use the communist upper bound, okay? All principal choices, no magic constants, no fudge factors, no tricks. Nothing up in my sleeves. All numbers were chosen in a principled manner. I'm gonna choose, split the difference and kind of right in the middle, that kind of stuff. Now, there's a dark horse in this that I wanted to share with you, which is I did this all with "it's not me, it's ChatGPT." This is a great breakup line, right? It's not me, it's ChatGPT. With ChatGPT, I used essentially I use it all the way for all the steps in doing this research. I've used ChatGPT. I use it for average number of comparisons. I did a lot of math for me. It generated a lot of code, a lot of experiments, a lot of timings, a lot of bugs. It actually did generate a few bugs. The plots were generated by ChatGPT and Wolfram Alpha, and this slide's title was suggested by ChatGPT. Oh, again with the horses. I mean, come on. Okay, this is crazy. And for more thoughts, bon appetit, everybody, and please come to my next talk, which is going to be focused on exactly this stuff after lunch. Get coffee. Thank you very much.